talking about the columnar stores today, and especially about optimizing columnar stores. It's quite a technical subject, so I guess half of the room is already left. But don't worry, bear with me. So, who am I? My name is Istvan Szukacs, and I work with data systems. I don't like to use the word big because it's, definition of big is different by companies. I used to work for Amazon, Riot Games, and also Symantec a little bit. And now we have a startup, basically an on-demand DevOps and data expertise company. Our clients are mostly in the US and Western Europe, but also we have some Hungarian clients. And we are building data pipelines and decision pipelines. Essentially, it's an end-to-end solution for companies who want to use data for their operations. Okay, so let's talk about a little bit about data stores. So we have the good old row-based data stores like MySQL, Postgres, all the SQL stores essentially, and they store the data as you can see, like in a row fashion. And there are columnar stores that store the data based on the different columns. So there are some implications for this that's probably not obvious just by looking at this picture. So what are the pros and cons for these technologies? So if you have a row-oriented database, then it's easy to add and modify records. So when you're issuing an update or insert statement, it's much easier for those stores. And the cons, you might read unnecessary data. If you are selecting, a subset of your columns, then you still read the entire column set and usually filter it out later. So that's, actually I kind of missed it, but the suite table for write heavy load is for the pros, obviously. And what's the column-oriented data store? So the pros are only need to read relevant data. So if you are querying, like, let's say, a couple of columns, and you have a huge amount of columns, it's going to be reading only those columns. And the downside that if you're updating rows in a columnar store, or let's say a row, then you have to update multiple files essentially, and that's probably the downside of that. So this one is suitable for read-heavy analytical load. Obviously, it's in the wrong position on the side. Anyways, the short history of columnar stores. So it's quite an old technology. The first design was about these systems in 1975 and in 1983 and 1986. And these systems, the first one is for a healthcare company or a biomedical research company. The second and the third one is developed by the defense forces of Sweden, actually. They wanted to store some data and wanted to read it like really fast. And this is the very first mention of columnar stores. So it's from the white paper. It was printed and scanned in later on because obviously in the 80s the white papers were typed in on a typewriter. So this is the first reference right here. The fully transposed file is the reference to a columnar store. And funnily enough, this fully transposed file is a reference to this white paper. It's done by a Hungarian guy, Don Steve Battery. He was working for the University of Toronto, and he came up with this. So the really important part is the body line. So each subfile contains selected attribute data for all of the records. So essentially, this is the definition of columnar stores, that you store in different files the attributes for the same table. Okay. So some notable features for these columnar stores. We can use some smart data encoding because in the same column, it's the same type of information. So you can have assumptions about like what you are going to be storing there, and then you can come up with smart data encodings, and that's really important for saving space. Also, you can have efficient compression because you have usually highly repeated values if you do it right, and that helps compression. And other fun part is that you can have lazy decompression. So when you are running a select against this database, usually the decompression happens at the client side. So you did the query on the server, and the server just sends you sort of an encoded compressed data, and you can decompress it on the client side. Okay, so let's walk through these features one by one, how it works, really. So I'm pretty sure that you are aware of that. There are different variable types that you can use in any data system. And this is like a rough estimate, like how much a certain value type is going to be in a data system. Obviously, storing the booleans are the cheapest because it's only 1 bit worth of data. Storing integers also quite cheap, it's 1 to 8 bytes, and so on. You are storing floats, it's 4 to 8 bytes. Datetime also very cheap. And when you are reaching the string line, that's what's really heavy on the databases, because it can have 1 to 4 bytes per character. So if you have like a 64 character long string, then it's usually like 64 to 512 bytes. So that's a huge amount of space compared to integers. So data encoding is about how to transform, how to store an integer, or how to store a string as an integer. That's pretty much the gist of it. So, and yeah, obviously there are complex data structures, and for those, the how much space it's going to be using, you cannot predict it, you have to measure it. Okay, so how could we store, let's say, strings as integers, right? So if you're assigning each distinct string an integer value, and you are creating a dictionary that's just referencing that string to an integer, this is how you can save the save space. So there's a real example, storing the SHA-2 hashes. That's quite a long string. It would be 64 to 412 bytes, but if you store it as an integer, then it's going to be 1 to 8 bytes per row. So storing the dictionary to enable this sort of encoding plus the data is usually much less than storing the unchanged data. So this is called the dictionary encoding, when you are creating a dictionary for that. So again, the dictionary contains the integers on one hand and the corresponding string values on the other hand. And in the database, you only store the integers, and when you need to actually read the string, then you go to the dictionary, do a reverse lookup, and get back the string. Most of the data systems today supporting this sort of encoding. Cool. On the top of that, what you can do, you can employ run-length encoding. So what does it mean? So imagine that if you have like repeated values in a column, let's say you have those 5 A's, and you store the A only one time, and you store the second value is like how many times it's repeated after that. So you can compress, repeated values quite a bit with run-length encoding, and this is also most of the data systems today support this sort of encoding as well. So there is only one thing to note here, that this works on sorted data sets only. If you have like ABC, 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 that's not going to be able to compress much for you. But if you have A, B, 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 C, 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 that's where you can actually save some space. And you can also employ this run-length encoding for multiple columns. Then you have to order by those columns as well. So it adds a little bit of complexity on the writing for the data files. Cool. So this is a real-world example for the run-length encoding. So I have 3 columns. I have repeated values. One column is text. Another one is integer. Third one is also text. This is the corresponding thing that you have to store. One thing you can note that it's much shorter than the original data set. So imagine that you have 1 billion rows with the same thing. You can save huge amount of space. Cool. And on the top of these data encoding techniques, you also have compression. So in the Hadoop world, mostly Snappy and Zlib is used widely. So you can trade sort of like insertion time versus space, like how much space you are saving. And Snappy is generally faster. It saves a smaller amount of space. If you have like time to compress your data better, then you can use Zlib, and it's much better space efficiency. Most of the other systems are already supporting these things. Cool, and then lazy decompression. So whenever you're running a query, you're going to get back your result set plus the dictionary, and you're going to expand the answer on your client side. So you can save bandwidth between the client and the server. This is also supported by most of the Hadoop systems today. And yeah, the downside is that you have to send the dictionary over to the wire to the client. But it's usually much smaller than the data, so it's no problem. So let's talk about like actual columnar stores. So LCFI, ORC, and Parquet now supported by Hive, and these are the corresponding versions when it was introduced. Facebook used lots of LCFIs earlier, and then they moved over to ORC recently, maybe 2 or 3 years ago. And Parquet is the new competitor on the market. It's supposed to be the fastest. I don't know if you ask me, there is very tiny difference between the ORC and the Parquet performance and save space saving, so you can use these files almost equally. So there is no big advantage or disadvantage any of those. So how does ORC look like? So this is how an ORC file looks like. There are many stripes in the file, so it basically splits up the data into stripes. It's called stripes. Usually the stripe size is 250 megabyte, and each stripe has an index, header, the data, that's actually the rows, and the footer, and this is repeating. And the index data basically has information about all the columns, and the row has also information that stores actually the data. This is how an ORC file looks like internally. Cool. So the best is to store the data between these files in a few stripes. And if you are using Hadoop, then it's a best practice to have a little bit smaller stripe size than the Hadoop HDFS block size. So one mapper can actually read at least a stripe, but also you can try to align it per file, but it's much harder. So usually the stripe size is adjusted to the Hadoop HDFS block size. The index has basic statistics, so for example, min and max. So if you're running a min, select min query against an ORC file, it won't read anything, it's just going to read the index and return it immediately to the reader. And the ORC file has almost all the things that we are talking about, plus some really fancy additional things. So, for example, it supports predicate pushdown. What does it mean? It means that when you are querying, when you have a select with a where clause, the where clause is sent to the reader. So the reader gets the where clause and only reads the data that it absolutely has to. So basically, you can decrease the amount of data that you are reading from disk. It also has Bloom filters. I don't know if probably you are familiar with Bloom filters. Also has lazy decompression that we were talking about. It supports Snappy and Zlib, has compression algorithms. It also has bucketing. Bucketing is a technique that you are putting the data into different buckets, but you have to enable sorting for that. So you have to sort your data based on one column and put it in many buckets. All right, so let's talk about the real-world use case. So our client was asking us to have a look to their columnar store that was ORC, and they had like lots of moving parts, and they had like 1 terabyte a day, roughly speaking. The table that we needed to optimize had like 83 columns. The cluster is like 1 petabyte full size, and it was snappy compressed. These were the input parameters. The thing is that we cannot or could not change something that would break the ETL engine or the queries. So we were asked to do changes that won't impact the running queries, even the running queries against the system, or they won't impact the ETL engine. And there was no explicit sorting in the data. It was quite funny when I figured it out. So basically they were missing out lots of optimization by not sorting the data at the insertion time. Because we learned it that if you sort your data, then you can apply, for example, the runtime encoding. But if you don't sort it, it cannot figure out like your, the stuff by itself. So this was a big optimization opportunity. And they had a few extremely wide columns, meaning that large strings, and high repetition. That's really important. They also had like high repetition. So we had a couple of assumptions. We had the assumption that the problem is I/O bound. What does it mean? It means that when you are reading the data, that's the limiting factor of your cluster performance. So decreasing the size on disk will result in better performance. So how can we ascend this without even looking at the cluster? The thing is that CPU capacity is outperforming the storage capacity and the storage performance for the last 3 decades. So it's not going to change any soon, meaning that the CPUs are developing much, much faster than the server disks, or the disk performance, or the capacity. So I assume that if I decrease the amount of data that we store on disk by better compression, then we're going to gain some performance even on the querying side. Cool. So I save you from the iteration steps. I had like, I don't know, like 6 or 10 iterations. So I ended up with the following changes. I explicitly sorted the data set by the widest column. And I also explicitly sorted the data set in the secondary and third and fourth position by the wider columns. I changed the compression algorithm from snappy to zlib. I changed the bucketing from 20 to 256. I won't go into details why that happened, but just bear with me. And I also changed the stripe size from 64 megabyte to 128 megabyte. That's the HDFS block size for that Hadoop cluster. And then let's see the numbers. So this is the, this is the table create statement. I didn't change anything else in the table definition, just enable the sorted, like you see there, the sorted by, there is the wider columns, into 256 buckets, and the table properties, it's ORC compress equals zlib, and the stripe size equals 128 megabyte. And that's it. Okay, so let's see the numbers. So the numbers, we had the baseline that was running for 84 seconds, reading 860 gigabyte of data. After my optimization, the query was running by 27 seconds, something, and the data size was 205 gigabyte. That's quite a bit of optimization. If you apply the same optimization to the petabyte scale, then you had the original data store with 1 petabyte, and after the optimization, it had only 250, roughly, terabyte information, the same data. So how did it happen? So essentially, enabling the sorting for on the widest column, enable the ORC file to compress it better, use a much better run length encoding on the file, on the data, and also like the compression algorithm change saved us this much. And the query performance went up as a side effect because I decreased the amount of data on disk. So we got the key changes and findings. So introducing explicit sorting, saving a huge amount of space. That's nothing else, just enabling sorting. That you can do, like you can just go to the table create statement and sort by the things that you want to sort by, and that's it. I traded some insertion speed for saving some space, so meaning that I think it was like 50 minutes with Snappy and 1 hour with zlib. So came quite close, but again, it saved us some space, so all of the select queries were running faster. It's a good trade-off. And saving space almost linearly corresponds with query execution speedups. So it means if you decrease the amount of disk usage, let's say 50%, then your queries are going to be running at 200%. So that's quite a good optimization. And disk I/O is still the biggest bottleneck for these large-scale data warehouses, as we just proved. And default settings are not good enough for petabyte-scale data warehouses. So if you are using any Hadoop system today, don't use the defaults. Like that's not good enough for you. You need to dig into the details. And you need to tune the cluster to your needs. And then you can save a huge amount of space, and that directly corresponds to a huge amount of money. And knowing the details of your columnar store helps what to change. So you really need to think about like crazy things. It's just simple sorting and choosing the right compression algorithm. But if you know the details, then you can change those things. And some companies don't quite aware of those details, so this is why they don't run their Hadoop clusters efficiently. And you can change things around without breaking anything. So I didn't break a thing. Like this cluster is still running in production as it is. Okay. Cool. And we didn't need to change any code. Like there was no code change. We just change the table create statements, and we iterate in again the same data, and that's it. So these are the key findings for this project. Okay, you can ask some questions, and I might be able to answer them. Thank you.
Questions? I have one. So, how long did it take for you to do the optimization? So the results sound very impressive, but
Yeah.
how many time did you spend on it?
So actually, I had 6 different tables. I experimented with 6 different tables, and I kept the experiments that yielded to better performance, and I combined them at the end. It took me 1 week to figure out like the details of the data store, another week to write the new table definitions, and we had like 2 weeks at the end of the project to communicate the changes to all of the corresponding teams and the senior leadership at the company. So altogether, it was a 1-month project.
What are your thoughts about profiling and debugging these kind of distributed systems? Because just to give you a concrete example, right now I'm heavily working on scoop development, and in the past 2 weeks I tried to figure out a very, very nasty performance issue, and it was terrible to find it.
Yes, so it wasn't trivial, but I had like a kind of leeway before I started the project. I spent 1 week before I started this project reading everything on the internet about like performance optimization on data warehouses. I read the most helpful one was the blog post from Facebook that's describing how they optimize a 300 petabyte data warehouse, and that has everything that you need to know. And after that, it was kind of easy to apply the same things that Facebook did and apply it to this client and to this data set.
Last question. Would you like to drink a palinka with us?
Yes.
So, thanks again for Istvan. Please give him a hand.